Hey everybody, now we're going to talk about how for a pretty large class of simple slope stability problems, instead of firing up commercial software to get a solution, we can simply do some very quick calculations with a set of charts and find the factor safety against failure for a slope. So chart solutions are covered in the appendix of your textbook, Soil Strength and Slope Stability by Duncan, Wright, and Brandon. And you can use them to calculate the critical factor safety for a pretty significant variety of simple problems, particularly with homogeneous slopes with simple geometry. They're especially useful for phi=0 or undrained conditions, which is primarily what we're going to focus on. And you can even use them for non-homogeneous cases if you average the strengths and the unit weights, which we'll talk about at the end of these slides. So, as I mentioned, there are a series of charts in the appendix of your textbook. They assume homogeneous conditions and provide adjustments for a number of factors, which we'll talk about. So this is the basic diagram of what we're talking about. You have a simple slope of height h. It's at a slope angle beta. Sometimes we talk about the slopes as b to 1, so a 2 to 1 slope would be 2 horizontal to 1 vertical, for example. It turns out b is equal to the cotangent of beta, and so we'll use the two of those a lot interchangeably. The height of the slope above the toe is h. If you have a firm foundation down at some depth, capital D, there are cases in which the critical circle will be tangent to that, as shown in this particular slide. And when we use the charts, there's be a lowercase d, which is called the depth factor, which is the ratio of capital D over h. If this foundation is right at the base, then the depth factor is 0. And you can solve a lot of problems that correspond to that condition. You can also come up with factors to account for partial submergence, where there's a certain water at a certain height above the toe of the slope, or above the base of the slope. You can account for surcharge along the top of the slope. It's assumed to act uniformly across the top. And then you can even have a small reduction for a tension crack. If we have cohesive soils up near the top of the slope, if you look at the slices, the cohesion can be greater than the effective stress or the horizontal shear or normal stress, and soil does not work well in tension, so we often just assume a tension crack forms there. In other words, we neglect the cohesion in that section, and we'll talk more about that later in the semester on how to solve for that using slope stability software. But you can do a factor for that as well. And so this is the equation that we use with these, and this term n naught comes from, we scale that off one of the charts, which I'll show you in a second. And then there's a C over PD term. C is the undrained cohesion. Again, we're dealing with the phi=0 case. P sub D is this factor here. It's equal to gamma h, which is h is the height of the slope, so this is kind of the weight of the slope. Q is the surcharge at the top, minus gamma water HW. This is the height of the water from submergence. And then we have these three adjustment terms on the bottom, mu Q, mu W, and mu T, are adjustments associated with the surcharge, submergence, and the tension crack, and they come from another set of figures in the appendix. If you don't have any adjustments, no submergence, no surcharge, no tension crack, just a really simple slope, then this equation simplifies to n sub naught times C over gamma h. And remember, C is kind of our force resisting failure, and gamma H represents our force driving failure, roughly speaking. So where do we get this n sub naught term? This is the primary chart used for the phi equals 0 case. And along the bottom we have the slope angle, and you can do that either in degrees or in the slope coefficient b, which is cotangent beta. So this would be a 1-to-1 slope, this would be a 2-to-1 slope, and so forth. So a 1-to-1 slope is 45 degrees, and so on. And then you go up and you pick the appropriate curve here, and then scale over and get a stability number n sub 0 to put into this equation. And the curve is a function of the depth factor. Remember, the depth factor is d over h. And so if the depth factor is 0, then we use this curve over here, which starts right here and goes this very top curve that says d equals 0. And we find the slope angle we have, come up to that curve and go over and find a stability number. And for any of the other depth factors, we just scale the appropriate one. There's something else shown on here. There are 3 kinds of circles that we talk about. A slope circle is when there's a firm foundation right at the very base of the slope, and the slope angle is not very steep, and the bottom part of that critical failure surface will exit somewhere above the toe of the slope. That's called a slope circle. And then a toe circle is where the critical circle goes right through the toe of the slope. And this can happen when, if the firmer foundation is a little bit deeper in certain combinations of slope angles, or for really steep slopes, which you'll see in a minute. And for more mild slopes, and if you have a deeper foundation, then the edge of the critical circle will exit somewhere along this line here, and that's called and it'll go all the way to the base of the firm foundation, and that's called a deep circle. And so yeah, this is how, using the depth factor and the angle, we get a stability number, and then these other terms, mu q, mu w, and mu t. I'm not showing the charts for those, but they're in the appendix. You can find those based on those other factors. Let's talk for a minute about the location of the critical circles. If you have a very steep slope where the angle is greater than 60 degrees, or the slope factor is less than 0.6, so 0.6 to 1 or greater, in other words, really steep slope, then you'll have a toe circle, and it'll go, no matter where this foundation is at the bottom, whether it's right here or deep, it will always go through the toe of the slope. And so we can guarantee that's a toe circle, and that corresponds to this region right down here. It's a toe circle. Doesn't matter what the depth factor is, it's always a toe circle. And but if you have a firm stratum right at the base of the slope, and then a milder slope that's less than 60 degrees, then that it won't be a toe circle, but this failure surface will exit somewhere up the slope, and it'll be tangent to the bottom here. This is called a slope circle. And then if you have a stronger material is deeper, and then an angle between 53 and 60 degrees roughly, you'll get a toe circle again, but it may pass down a little bit into the foundation, but it's still a toe circle. And then there's kind of this middle ground between 43 and 53 degrees where you could have a local minimum with a toe circle and another one with a depth circle. So you just look at, or a deep circle, you just look at both cases and use the smaller factor of safety. And then finally, for slopes milder than 45 degrees. Now I should just add, most of the slopes we deal with, certainly engineered slopes, are going to be milder than 45 degrees. I mean, not always, but a lot of our slopes we deal with are more mild like this. In this case, if there's a bedrock or firmer stratum at some depth, the critical circle will always go down to that depth, and then it will exit somewhere along this line over here, and that's what we call a deep circle. Finally, if you have multiple materials, you can still use these charts. You just have to come up with an average cohesion and an average unit weight. To get the average cohesion, you use a weighted average of the two cohesions, and it's weighted based on how much of the material is in each of these. And so it's shown here based on this angle. I don't know if you'd need to actually go to the effort of calculating those angles. You could just eyeball this length and do a weighted average. And then for the unit weight, it's more an average of how much of this material, how much of the sliding mass is in each material. So for this case, I would say, this upper material is about the same area as the lower material, so I'd maybe equally weight the unit weights, because the unit weights drive the weight of the soil. But if it gets too complicated, just forget the charts and use slope stability software. But in a pinch, you could do something like this. And in summary, these slope stability charts are really handy, fast and convenient way to calculate the factor of safety without having to fire up the software.